Now, in a similar way, whenever I have a charge moving with a certain velocity through a magnetic field, say that our magnetic field is in this direction, then it's going to feel a force that, in this case, is up. All right? So I have this charge moving with a certain velocity through a magnetic field, and it feels a force. Well, let's imagine that instead of just having this charge moving freely, let's imagine that this charge is actually moving into a wire, all right? Is moving in a wire. And so when I have this charge moving with a certain speed through this wire, think current, through a magnetic field, then that current, that wire will actually feel a force inside that magnetic field, right? Now, a current in a magnetic field experiences a force. The magnitude of that force is going to be the current times L times B times sine of theta. We can think about this in terms of just dimensional analysis to our previous expression, QV cross B, or QVB sine theta. We can see that Q and V have the same units as I and L. If I remind you, I is coulombs per second, L is meters, Q is coulombs, this is meters per second. So notice that the units here are the same. So basically we're dealing with the same phenomena, except now instead of talking about free charges, we're talking about charges moving along a wire. So we have charges moving with a certain current through a wire. That wire is inside of a magnetic field, and that causes a force on the wire. All right, so as I said, charges moving in a wire feel a force. Force is transferred in a wire. And also remember that when we talk about current, we're talking about the direction of flow of protons. So we will continue that facade, assuming that current is the flow of protons, not electrons. So for example, let's say I think this is the same situation we had up here. Let my fingers go in the direction of V, or in this case, in the direction of the current, right? And then they fold towards the magnetic field. The magnetic field is into the page, or the magnetic field comes out of your palm, and then the force is going to be in this direction. Or more particularly, the force is going to be on the wire in this direction. I have a little clip here, or I think I have a clip. I will try to find it. And it just shows how this force, you can see this, you can do this experiment at home on your own, but how you can see this force acting on a current carrying wire within a magnetic field. So you can just watch this. It's not very long. You can watch it here. Now, let's just do some examples. Let's find the direction of the force for these configurations of a current carrying wire in a magnetic field. All right, so first, remember F equals I L B sine theta. All right, so we're going to have the same thing here. We'll let our fingers go in the direction of I. We'll let our palm point in the direction of B, or if you prefer, let your fingers fold towards B. I think I kind of prefer the palm. And then our thumb will give the force. This is the same application of the right-hand rule that we had before. The only difference is instead of letting our fingers go in the direction of V, our fingers are now going in the direction of I. But it's really the same thing because their charge is moving with a certain speed, except they're moving within a wire. So here I'll let my fingers of my right hand go in the direction of I. B has to come out of my palm, so I have to sort of flip my hand around. And then what's the direction of the force? Well, we know that the force can't be in the X direction, and it can't be in the Y direction. So it has to either be into or out of the page. Fingers in the direction of I. B is up. So that makes my force into the page. Here, I is down, so fingers point down. B is into the page, right? I know what axis must my force lie upon. Is it the X, Y, or Z? Okay, well, this is my Y-axis right here. It's already taken up. B is along the Z-axis, so it has to be the X-axis. So it's either left or right. Fingers in the direction of I, B is into the page, so the force on this wire is to the right. And here, finally, I is up, B is out of the page, and so the force here is to the right. All right, let's try this quick test. Remember, F equals ILB sine theta. and we will come back to this.